This is example problem 927. The problem reads, if the boundary layer on the hood of your car behaves as one on a flat plate, estimate how far from the front edge of the hood the boundary layer becomes turbulent. How thick is the boundary layer at this location? Now, as it's written, this problem is a little abstract, but what we can do is add some detail to make it a little more concrete. So if we make the car's speed, u, equal to, say, 60 miles per hour, this is equal to 88 feet per second. Now we can actually calculate values for the critical length and the boundary layer thickness. And while we're at it, we'll also calculate the wall shear stress. So if this is in feet per second, our unit system is British gravitational units. And the idea is to find the critical length, or the length at which the flow becomes turbulent, the boundary layer thickness, delta, and the wall shear stress, tau wall, at that point. If we draw ourselves a picture here, we've got the hood of the car, windshield, top, back window, trunk, etc. Some snazzy wheels here. And we draw the velocity profile for an inviscid flow here at some speed u. And we look at the flow over the hood as being the flow over a flat plate. Now if we zoom in here, and we treat this as a flat plate, not as the hood of a car, and we start at the origin and move in some x direction here, we know that the boundary layer slowly increases and the resulting velocity profile looks something like this. So our solution is fairly straightforward in this case, just a couple of equations here. But before we start, we should list the properties of air that will be relevant to the calculation. The density of air is 2.38 times 10 to the minus third power. And this has units of pound force second squared per foot to the fourth. The absolute viscosity is equal to 3.74 times 10 to the negative seventh power, and this has units of pound force seconds per foot squared. And the kinematic viscosity, nu, is equal to 1.57 times 10 to the negative fourth power, and this is units of feet squared per second. Okay, so the first thing that we're going to try to find is the critical length. And the relationship for that is simply the definition of the Reynolds number with respect to x, where x is the characteristic length, and specifically the critical length. And so this is equal to x critical, the characteristic length, times the velocity of the flow over the plate, u, divided by nu. And if we rearrange this, we get x critical is equal to the Reynolds number with respect to x critical times the kinematic viscosity divided by the free stream velocity. And we'll take the critical Reynolds number to be 5 times 10 to the 5th. And this is stated on page 502. So this then just becomes a plug and chug exercise. X critical is equal to 5 times 10 to the 5th times nu, which is 1.57 times 10 to the negative 4th. This is feet squared per second. This is divided by the free stream velocity, which is previously stated is 88 feet per second. Feet cancel, seconds cancel, I'm left with 1 foot, which is of course the units that we'd expect for X critical, and this works out to be 0.89 feet. So a little less than a foot down the hood, the flow becomes turbulent, which means that the flow over the majority of the hood is turbulent. Next, we'll calculate the boundary layer thickness. And the boundary layer thickness, according to equation 915, is 5 times the square root of nu times x divided by u. And this, again, is just a plug and chug exercise. We have 5 times the square root of nu, which is 1.57 times 10 to the negative 4th feet squared per second times 0.89 feet over 1, the result of the last step, divided by 88 feet per second. Extend the radical here, avoid confusion. So we've got feet cancels here and here. We've got seconds cancel here and here. If we take the square root of feet, we get feet. And this works out to be 0.0063 feet. And this is equation 915. Okay. And for the last part, to calculate the wall shear stress, tau wall, we simply use equation 918, which says tau wall is equal to 0.332 u to the 3/2 power times the square root of rho mu over x. And this is, as I said, equation 918. So we have 0.332 times 88 to the 3/2 power feet to the 3/2 power per second to the 3/2 power. We'll extend this one. And this is times the square root of rho, which is 2.38 times 10 to the minus 3rd pound force second squared per feet to the 4th times mu, which is 3.74 times 10 to the minus 7th pound force seconds per foot squared divided by x, which is 0.89, and this is feet over 1. And we take the square root of all of this. Now, you might be inclined to avoid the units since they are a little messy here, but I want to show you that they work out just fine. So if we take a brief aside here and we look at the units, we have pound force times pound force, which gives us pound force squared. We have seconds squared times seconds, which gives us seconds to the third. We have feet to the fourth times feet squared, which gives us feet to the sixth, divided by feet, or times 1 over feet, which gives us feet to the seventh. If we take the square root of all of this, and we multiply by feet to the 3/2 over seconds to the 3/2, we of course end up with feet to the 3/2 divided by seconds to the 3/2 times pound force, seconds to the 3/2 divided by feet to the 7/2. The seconds to the 3/2 both cancel. We've got pound force here, and we can further simplify here by looking at these two terms. If we write this as feet to the 3/2 minus 7/2, it's clearer to see. And I guess we could put a parentheses around there to make it a little simpler. And so this equals feet to the minus 4/2, or feet to the minus 2. And so this all works out to pound force per foot squared, which is what we'd expect the units for tau wall to be. So this all works out unit-wise, and we end up with tau wall being equal to something I didn't write down. Wait one. Tau wall is equal to 0.27 pound force per foot squared. So to recap, we've got a flat plate with flow at 60 miles an hour, or 88 feet per second. We use the definition of the critical Reynolds number to calculate the distance at which the flow goes from laminar, where it starts, to turbulent is just a little less than a foot, which means that the majority of the flow over the hood is turbulent. We use equation 915, which gives us the thickness of the boundary layer, this distance right here, at a horizontal distance of 0.89 feet. The boundary layer thickness is 0.0063 feet, very small. We use equation 918 to calculate the wall shear stress, and we arrive at 0.27 pound force per foot squared. And you can see that even though we have a messy exponent here and potentially a messy exponent here as to the 1/2 power, that all of the units actually do work out.